In this video, we're going to start the KutaSoftware Infinite Geometry free worksheet Probability with Combinatorics. Our directions are to find the probability of each event. In number 1, it says Beth and Shayna each purchase 1 raffle ticket. If a total of 11 raffle tickets that are sold and 2 winners will be selected, what is the probability that both Beth and Shayna win? Well, let's first calculate the number of possible combinations that there are. Because order does not matter in this, there will be 11 C2 or 11 choose 2 different combinations of choosing 2 tickets out of the 11 total. And Beth and Shayna are 2 choose 2. Because out of their 2 tickets, we're assuming that both of those get chosen, and that's going to be divided by the total amount of combinations out of those 11 tickets choosing 2. So 2 choose 2 will give us 1, and when we calculate out 11 choose 2 using our calculators, 11 choose 2 equals 55. So we have 1 out of 55, or 1 over 55 is the chance that they will both be selected. So 1 divided by 55 is approximately 0.01818, and in percentage form, since we want the percent, since we're talking about probability, that will be, moving the decimal place over twice, 1.818%. So they have less than a 2% chance of both getting chosen out of 11 raffle tickets. In number 2, a meeting takes place between a diplomat and 14 government officials. However, 4 of those officials are actually spies. If the diplomat gives secret information to 10 of the attendees, at random, what is the probability that no secret information was given to the spies? Again, order doesn't matter when we decide the different combinations, therefore we're going to be using NCR. Now, there's a total of 14 government officials, and the diplomat gives secret information to 10 of those. So 14 choose 10 is the amount of total combinations that there are choosing 10 of those 14 people. However, 4 of those are actually spies, so we're looking for the probability that no secret information was given to the spies. So if no secret information was given to the spies, that means if we subtract out those 4 spies, 10 people are not spies. So out of those 10 people, we choose 10 of them. Or we choose those 10 that are not spies. So 10 choose 10 is equal to 1, and 14 choose 10 is equal to 1001. So if we take 1 and divide that by 1001, we get 0.0001. We will get approximately 0.1% when we change that decimal into a percentage. In number 3, it says that a fair coin is flipped 10 times. What is the probability of the coin landing heads up exactly 6 of those times? So if a coin is flipped 10 times and there's 2 options each time, that's either heads or tails, that's going to be 2 to the 10th different possibilities. And out of those 10 possibilities, we're choosing that the coin lands heads up exactly 6 times. So that will be 10 choosing 6, where those 6 are heads. So 10 choose 6 is equal to 210, and 2 to the 10th is equal to 1024. Both of those are divisible by 2, so simplifying this fraction, 210 divided by 2 is 105, and 1024 divided by 2 is 512. If we take 105 and divide it by 512, we get approximately 0.20508, which when converted to a percentage is 20.508%. Because we're calculating for the decimal of this fraction and then moving that decimal point over 2 times to the right to get it in percent form, or simply multiplying by 100. Number 4, a 6-sided die is rolled 6 times. What is the probability that the die will show an even number exactly 2 times? Well, one way we can think of this problem is that on a die, the numbers are 1, 2, 3, 4, 5, 6. If we split those up into two separate categories, there's either odds, 1, 3, and 5, or there's evens, 2, 4, and 6. So the possibility of odd versus even on a 6-sided die, the number of combinations of odd or even will be 2 to the 6, since we're rolling the die 6 times and there's two different options, either odd or even. Now we're looking for the probability, though, that the die will show an even number exactly 2 times. So out of those 6 times, we're choosing 2 times that it will be even. 2 to the 6th is in the denominator, and that's 64. And 6 choose 2 is in the numerator, which is 15. So 15 divided by 64 is 0.234375, which, when converted to a percentage, is approximately 23.438%. And again, we were able to do 2 to 6 different possibilities because we looked at the die as opposed to 6 separate individual numbers. We looked at it as 2 groups of numbers, odd or even. That's why the base with our exponent was 2 for the 2 different choices. In number 5, a test consists of 9 true-false questions. A student who forgot to study guesses randomly on every question. What is the probability that the student guesses at least 2 questions correctly? So because it is either true or false, we again can use 2 as the base of our exponent. And there's 9 questions total, so that's 2 to the 9th different possibilities of answers. And we're looking at the probability that the student gets at least 2 questions correctly. So that's getting 2 correct, 3 correct, 4 correct, 5, 6, 7, 8, or 9 out of the 9 total. So that's going to be 9 choose 2 plus 9 choose 3, getting 3 correct, plus 9 choose 4, getting 4 correct, plus 9 choose 5, 5 correct, plus 9 choose 6, getting 6 correct, plus 9 choose 7, plus 9 choose 8, plus 9 choose 9. Because remember, getting at least 2 questions correct means that he either got 2 or 3 or 4 or 5 and so on. And you can think about a probability formula. If we're looking for the union, the probability of A or B, we're going to be adding those probabilities together. But this is all over the possible number of combinations. So 9 choose 2 plus 9 choose 3 plus 9 choose 4. Adding all of those combinations up, we will get 502. And that's out of 2 to the 9th different combinations, 512. So 502 different combinations of getting 2 answers correctly over 512 possibilities of answering the test. We can simplify that fraction, dividing both by 2 into 251 all over 256. And 251 divided by 256 is equal to 0.980468, which rounds to 47. But turning that into a percent, moving the decimal place over twice, that's 98.047%. So the student has roughly a 98% chance or 98% probability of getting at least 2 questions correct. In number 6, a basketball player has a 50% chance of making each free throw. So the basketball player, since it's 50% chance, that's 1/2. So he's either going to make it half the time or miss it half the time. What is the probability that the player makes at least 11 out of 12 free throws? So if he's making a total of 12 free throws, that'll be 2, because he's either making it or missing it, to the 12th. That's the number of different possibilities or different combinations of making and missing the shots. But remember, we are looking for the probability that the player makes at least 11 out of 12. So that's either he makes 11 or he makes 12. So that'll be 12, choose 12 if he makes all 12, and we're going to be adding that, since it's either 11 or 12, to 12, choose 11. 12 choose 12 is 1, plus 12 choose 11 is 12, and that's all over 2 to the 12th, which is 4,096. So that's equal to 13 all over 4,096. 13 divided by 4,096 is equal to 0.00317, which, when converted to a percentage, is 0.317%. So remember, we have to move the decimal place over twice when dealing with a percent. And if you want me to write the decimal out, that was 0.00317. So we moved it over twice to get 0.317%. Number 7 says, a technician is launching fireworks near the end of a show. Of the remaining 14 fireworks, 9 are blue and 5 are red. If she launches only 6 out of the remaining 14 in a random order, what is the probability that exactly 4 of them are blue? So she's only launching 6 out of the total 14. So out of the possible combinations, we have 14 and we're choosing 6. Now, an important part of this question to note is we're looking for the probability that exactly 4 are blue. So that means that 4 of them will be blue, and the remaining 2, since there's 6 total, the remaining 2 will be red. So we have 4 blue and 2 red. So remembering our probability, the probability of A intersection B, or A and B, is the probability of A times the probability of B. So unlike the previous problems, such as number 5 and 6, where we were adding the combinations, now we're going to be multiplying. So the chance that we get blue, if there's 9 total, and we're looking at getting 4, that's going to be 9, choose 4. So we're going to be multiplying the different combinations of getting blue by the different combinations of getting red. So if there's 5 red total, and we get 2 red, that's 5, choose 2. So looking at our specific combination of blue and red, and dividing that by the total combinations, that will give us the probability of exactly 4 blue and 2 red. But more importantly, 4 blue. 9 choose 4 is 126, and we're going to be multiplying that by 5 choose 2, which is 10. And that will all be divided by 14 choose 6, which is 3,003. So 126 times 10 is 1,260, and we're dividing that by 3,003. 1,260 and 3,003 can be simplified because both are divisible by 21. So that will be 60 over 143, which, as a decimal, 60 divided by 143 is 0.41950, so 58. And converting that to a percent, moving the decimal place over twice, that will be 41.958%. So there's almost a 42% probability that exactly 4 of those fireworks will be blue. And number 8, a jar contains 10 black buttons and 6 brown buttons. So if we have 10 black and 6 brown, that's going to be a total of 16 buttons. If 9 buttons are picked at random, what is the probability that exactly 5 of them are black? So if exactly 5 are black and we're picking 9 total, that means that 4 have to be brown. So there's 5 black and 4 brown out of the total combination of buttons, which we're choosing 9 out of 16, so 16 choose 9, choosing 5 black. If 10 are black, we're going to have 10 choose 5 because we only want 5 black, and out of the 6 brown, we're choosing 4. So that's 6 choose 4. So the different combinations of choosing 5 black buttons out of the 10 black buttons times the combinations of choosing 4 brown buttons out of 6 all over the different combinations of choosing 9 buttons total. 10 choose 5 is equal to 252, and we're going to be multiplying that by 6 choose 4, which is 15. So 252 times 15 all over 16 choose 9, which is 11,400. 3,440. So 252 times 15 equals 3,780. 3,780 all over 11,440. Now both of these are divisible by 20, so we can simplify this fraction, dividing both by 20. 3,780 divided by 20 is 189, and 11,440 divided by 20 is 572. Writing that number as decimal form, 189 divided by 572 is equal to 0.330419, which rounds to 0.42. In percent form, that's 33.042%. So roughly a 33% chance that out of the 9 buttons we choose from that jar, 5 of them are black. And that's exactly 5. In number 9, it says that you are dealt 5 cards from a standard and shuffled deck of playing cards. So all the cards have the exact same probability of being drawn. So the question we're asked is, what is the probability that you'll have at most 3 kings? So that means we could have 1 king in our hand, 2 kings in our hand, or 3 kings in our hand. However, since there's 4 kings total, it would be much easier to subtract the probability from 1. So let's look at the chance that not at most we'll have 3 kings, but that we will have more than 3 kings. So if we have more than 3 kings, that's saying that we have 4 kings in our hand. So essentially, as opposed to looking at the probability of A, we're going to calculate the probability of not A in order to find A. So at most 3 kings, that's our probability of A, but we're going to be calculating the probability of not A, which is 4 kings in our hand. So let's look at the different combinations of being dealt 5 cards. That's 52 cards total, and we're choosing 5 of those. Now if we have 4 cards in our hand, that eliminates 4 out of that 5. However, we also have to eliminate 4 out of the total cards. So 5 minus 4 is equal to 1, and 52 minus 4 is equal to 48. So if we know that we have 4 kings in our hand, we're only going to look at 48 other cards, and we're choosing one of those 48 other cards to make 5 cards total. So 48 choose 1 over 52 choose 5. That is 48 all over 2,598,960 different total combinations. Now this is P. That's the probability of not A. So having 4 kings in our hand. But we want to find the probability of A that will have at most 3 kings. So if we take 1 and subtract not A, we'll get the probability of A. So we're going to take 1, which in order to add or subtract fractions, we need a common denominator. So my number 1, I'm going to write as 2,598,960 divided by 2,598,960 minus 48. And because I was subtracting over that same denominator, I just wrote this as one single numerator. So that's going to give me 2,598,912 out of 2,598,960. Now we can simplify those fractions to be 54,144 all over 54,145. And that's dividing each of those by 48. So the numerator divided by 48 will give us 54,144, and the denominator divided by 48 will give us 54,145. And converting the decimal form of that into a percent, we get approximately 99.998%. So that's the probability that we have at most 3 kings in our hand. So that's saying that we either have 0 kings, 1 king, 2 kings, or 3 kings. In number 10, it says a bag contains 6 real diamonds and 5 fake diamonds. So the bag contains a total of 6 plus 5 diamonds, which is 11 diamonds. So if 6 diamonds are picked from the bag at random, what is the probability that at most 4 of them are real? So if the probability at most is 4 of them are real, we can think of that as P of A. P of A is that at most 4 of them are real. So we're going to have the probability of A equal to 1 minus the probability of not A, which the different combinations for not A, we can either have all 6 diamonds real, or we can have 5 real. But remember, if we have 5 real, we have to calculate the different combinations of 5 real and 1 fake. So we're going to have 1 minus the probability of not A, the different combinations of real, 6 choose 6, since there's 6 real diamonds, plus 6 choose 5 times 5 choose 1. And that's going to be all over the different combinations of choosing 6 out of the 11 diamonds. Scrolling down so that I have more room to work, we're going to have 1 minus 6 choose 6 is 1, plus 6 choose 5 is 6, times 5 choose 1 is 5, and that's all over 11 choose 6, which is 462. So that's going to equal, I'm going to put these in a common denominator, so 1 will be 462 over 462, but remember we're subtracting 1 plus 6 times 5, which is 1 plus 30, or 31. So 462 minus 31 is 431 all over 462. That's the probability of our event occurring, which 431 divided by 462 is 0.9329. That's the approximation of that decimal, and converting that to a percent, we'll have 93.29% for the last problem on this worksheet. If you have any questions, leave them in the comments below. And as always, like, subscribe, and share. All likes and subscriptions are greatly appreciated, and let me know that you're finding these videos useful.